All right, welcome back. This is part 2 of Are You Ready? A chemistry review. We left off last part talking about electronegativity, what it is and what it means, and a little bit about electronegativity numbers and how it trends in the periodic table. So we're going to continue down that idea and look at what happens to compounds that have particular electronegativities. So if we happen to have a compound form where the atoms have equal electronegativity, which happens in the case of diatomic molecules, then we get what we call non-polar covalent bonds forming between them, between the atoms, and we get a molecule that is non-polar. Hydrogen here in the graphic is a good example. So hydrogen to hydrogen, obviously with two hydrogens, they're going to have the same electronegativity number. So the difference between them is 0. And that means that the electrons are going to spend equal amount of time between each of the hydrogens in the hydrogen molecule. And you learned in grade 10, and I'm sure did more work in grade 11, on the diatomic molecules, and we understand or I think memorize or can pick them out from the periodic table by using the hockey stick puck way of remembering, or perhaps something like an acronym like Hofbrinkel to remember which of the elements form those diatomic molecules, which are nonpolar and are formed from nonpolar covalent bonds. Another thing that can happen with polarity is that you can have polar molecules and you can have non-polar molecules, both of which are going to have polar bonds, but the molecules themselves end up being non-polar. So the graphic here is a good one because it shows both of those situations. So on the far left, we see hydrofluoric acid, hydrogen and fluorine together. And if you have a periodic table handy, you can see that fluorine has a much higher electronegativity than hydrogen does, thinking about which side of the periodic table they're on. And so the electrons will spend most of the time around fluorine, and that end becomes slightly negative, and the hydrogen end becomes slightly positive. So it is a polar molecule. It has poles, one positive, one slightly negative. Water also has that happen. The oxygen has a much higher electronegativity number than hydrogen, and even though the bond again is covalent, the electrons spend more of their time around the oxygen, creating a slightly negative side, and the hydrogen creating a slightly positive side. So polar molecule. The example on the far right, the carbon tetrachloride. What happens there, again, is you've got a difference between carbon and chlorine in terms of electronegativity numbers. It's not as big a difference as you see perhaps between hydrogen and oxygen, for example, but there is a difference between them. But because of the shape of the molecule, so when you look at all of these chlorines, they form with equal bond angles to each other, and in fact if you make the model, build it with a model building kit, you'll see that it doesn't matter which way you turn it, it always looks the same. It has that tetrahedral sort of structure. So even though it has 4 slightly polar bonds, there is no one side of the structure that ends up sort of continuously being negative or positive. The electrons are shared pretty equally amongst the 4 chlorine that are there. So with the shape and the small polarity in the bond, we end up with a molecule that is nonpolar even though it has polar bonds. Okay, as mentioned in the previous slide, polar covalent bonds occur when we've got atoms in a compound that have different electronegativities, and the water molecule is a good one as an example for us in biology. And again, we see the symbol there for slightly negative on the oxygen side of the molecule and slightly positive on the hydrogen side of this molecule. That little symbol means or gives us that idea that it's not a full charge, it's just a partial charge. All right, now we're going to move completely away from kinds of chemical bonds, and we're going to look at physical bonds. So we've got three kinds of physical bonds that are listed here: Linden forces, dipole, and hydrogen bonds. And all three are sort of broad categories of physical bonds, which I'm sure you will discuss perhaps more in chemistry. For our purposes, really, the one that's going to keep coming up over and over again is the idea of a hydrogen bond. Keep in mind here it's a physical bond, so it's not happening within a chemical compound. What we're looking at is slight attractions that occur between molecules. And they're weaker than ionic or covalent, but they can still have a big impact, biologically speaking. So in this diagram or graphic that we have here, we've got an illustration with two polar molecules. We can see the slightly negative, slightly positive ends, and then we can see that the slightly positive end of one is attracted to the slightly negative end of the other, and that's the purpley pink line that's there is supposed to illustrate that attraction. So for us, the most important example is water, and you've run into this concept a couple of times already, even if you never thought of it in terms of polarity. So in this diagram, we can see the slightly negative end, slightly positive end of the water molecules. We see obviously oxygen in red and hydrogen in blue. And the chemical bonds are drawn in solid lines, and the physical bonds are drawn in dashed lines. So because there is a slightly negative and a slightly positive end of a water molecule, it's attracted to other water molecules that have the same thing, the negative of one being attracted to the positive of the other. And they form quite a significant bond strength. And anybody who's sort of crashed into a lake and done a belly flop has experienced how powerful those bonds can be. And any of those little bugs you see walking along the surface, where the surface tension is actually stronger than pressure pulling down, or the gravitational pull on that insect, so it doesn't actually pierce the surface of the water. You also learned a little bit about this phenomena last year when you were in biology, and you were talking about how water moves in plants, where you learned about adhesion and cohesion, both of which occur because of the polarity of the water molecule. So we're illustrating only hydrogen and oxygen here, but please note that we get hydrogen bonds that will occur in molecules that are not just made of oxygen and hydrogen, but could also be hydrogen, nitrogen, hydrogen, fluorine, and so on. So anything that's going to create that polarity in the molecule can result in physical bonds between the molecules with those polar areas. Right, we're moving on to molecular structure now, and molecular structure in biological systems is quite important. If it's not the right shape or the right version of a molecule, then it may not be biologically active, or it may have unanticipated consequences. So in order to express the molecular structure of any particular compound, we can use the molecular formula or possibly the structural formula, depending on what we're trying to show. The molecular formula is going to tell us what kind of atoms are there and how much or how many of each kind of atom is present in the compound, where a structural formula will do that and also show us the arrangement of the atoms in that compound. So if we were to look at something simple like water, if we didn't know anything about chemistry and the way that atoms behave, we may think that the two hydrogen come sort of first. So hydrogen bonded to then the oxygen in sort of some kind of linear formation, where if we were given the structural formula, we would see that the oxygen is sort of our middle piece and our two hydrogen are bonded to that. The molecular formula can be used to show a little more information. For instance, if we were looking at the second example that popped up here, we can see that all three of these are portraying or showing the exact same molecular formula, so C2H6O. But the kind of information that we get from the different versions that are given here are a little bit different. So if I look at this molecule, the very first example, C2H6O, I may have several different kinds of compounds, molecules that I could draw from this particular molecular formula. And they could have different functions depending on where that oxygen was located. Where if I look at the final part of that example, so the third example of that, where it is CH3CH2OH, if I know something about functional groups, then I know it is an alcohol, and I can anticipate where the OH group is going to be attached in terms of which carbon, and pretty much what that will look like. Now, maybe not exactly, but certainly a lot more sure of it than I would be with the first one. So molecular formula can give us more information depending on how it's been written. The structural formula is useful for us in this in the biochemistry that's going to be coming up, because we're using or going to be dealing with mostly covalent bonds. We're looking at situations where we could have single, double, or triple bonds with the same kinds of atoms in play, and it's important that we understand, or that we know sometimes where those bonds are. They're going to have some impact on shape and functionality. Our final topic is isomers, and isomers are molecules that have the same molecular formula but a different structural formula, and we can sort of put those under two broad categories. One is structural isomer, the other one is stereoisomer, and it does get more complicated than that, and I'm sure perhaps the way you've dealt with this in grade 12 chemistry, if you've done that. If you haven't done grade 12 chemistry, this is probably a new concept for you. Perhaps you've done a little more detail there, and if not, I'm sure that you will do when you move on to university. So isomers are very important in biological systems, because certain versions of a molecule may be biologically active, and the other version of that may not be. So as a for instance, you may be looking at a particular kind of sugar, like a glucose molecule, and you may think there's only one kind of glucose molecule, but in fact there's an alpha glucose and there is a beta glucose. One of those kinds of glucose molecules is digestible by people and forms the basis for most of our starches that we can eat, and the other is indigestible except for a few bacteria and small critter insects and so on. And in that case, it's a primary component of cellulose, which is structural material, and you guys learned a little bit about that in plants last year. So they're both glucose, but they're isomers of each other, and what we can do with them in terms of digestion is very different. So isomers are quite an important idea. So structural isomers have the same molecular, but they both do have the same molecular formula, but they're generally look quite different in the way that those atoms are arranged, where a stereoisomer, again, same molecular formulas, but the differences are a little more subtle and reflect things like just maybe the same things are attached to one group, say a carbon, but are arranged in space slightly differently. So a good illustration of a structural isomer is glucose and fructose, both C6H12O6. And a good illustration of a stereoisomer is glucose and galactose, again, C6H12O6, but they look quite different. If you look at the graphic that's just popped up at the bottom here, glucose is over to the left-hand side, and if you take a close look, or actually if you take a quick look, it looks like glucose and galactose are the same molecule. If you look at the ring structure, it looks the same, the 5 carbons inside with the oxygen kind of holding it together. And if you look at carbon 1, 2, 3, and 5, you can see that the arrangement is identical. Our difference occurs in carbon number 4, where we have our OH group and our H group exchanged. And even though in both cases they're attached to the carbon, the functionality of those things are very different. One thing I will point out here is the graphic for galactose here is not great. Please note that carbon is not attached to the hydrogen and then hydrogen to oxygen. The line really should go to the oxygen in that carbon number 4. The other comparison here, glucose to fructose, we can see that they're visually very different. So this is our structural isomer. We can see that they look quite different, where galactose and glucose are stereoisomers. And we can see that fructose has a 4-carbon ring with 2 carbon groups hanging off, and the arrangement looks quite different. All right, we've come to the end of our first PowerPoint. Please write down any questions or concerns that you have and be ready to discuss in class tomorrow.